Now we begin to introduce the second part, the three linear motion. The linear motion can be divided by three conditions, where the acceleration is a zero, or a constant, or is variable. So from this point, we can divide into three motions: constant velocity, constant acceleration, and variable acceleration. In a constant speed, a constant velocity movement, the direction and the speed of the particle motion is unchanged. For example, if a train, I did not draw very well. If a train was going in a flat railway in a long time, it can be seen as almost a constant velocity movement. When a sphere going downwards on an inclined phase, and then it moved to a horizontal phase, has a velocity v0. Then if the phase is like have very little friction, then it may be considered almost as a constant velocity. If the rain is falling off from the clouds, the speed increases from 0 to a certain speed vf, and it can be considered will not change any longer. So that after this period of time when it's moving with vf, it can be considered as almost a constant velocity linear motion. And what is like a limited speed? That's the final speed. The larger the size of the rain, the larger the final speed. It is exactly the final speed that make the rain won't harm people, because it won't go up above that speed. So for the constant acceleration linear motion, the acceleration is a constant. We can note acceleration equals a0 is unchanged. So if t0 equals 0, the speed of the velocity, of that particle is v0, and it's at a position x0, then we can see from the previous video that v equals v0 plus t0 t at dot dt, this equation, we can see that v0 plus a0t equals our v, right? Because at is now unchanged, equal to the constant acceleration a0. And then we can refer to the previous equation that xt equals x0 plus integral t0 to t vt dot dt. We can substitute this v here so that we get x equals x0 plus v0t plus 1/2 at squared. And then we can use the equation about the derivatives, the relationship, that a0 equals dv dt equals dv dx the dx dt equals dv dx the v. And this is also very important. This substitution is frequently used in the competition physics. We will see that a lot later on. So that we integral on both sides, that v0 v dot dv equals integral x0 x a0 dot dx. Since a0 is a constant, we can get a following relationship, that v squared, which is now a function of x, equals v0 squared plus 2a0 times x minus x0. So what we discussed before, that you throw an object upwards, it is a constant acceleration linear movement, which the acceleration is downwards, equals g equals a0 equals 9.8 meter per second squared in magnitude. So that after the object is injected upwards, the speed goes down linearly with time, so that it reaches 0 at its highest point. And then the velocity becomes downwards. And the velocity, the magnitude, the speed linearly grows. And when this time period is after it's reached the highest point and then it goes down, in this period's time it's called free falling. Similarly, the wooden box that moves on an inclined surface, it's a linear constant acceleration movement too. If the friction is the same on this inclined surface. And if there was no friction, suppose this has an inclined angle of phi, then its acceleration is g sine phi. Another case, we can consider the variable accelerating. In a variable accelerating case, the acceleration is a variable, is no longer a constant. It appears most frequently in our world, which it has a lot of factors that affecting the object's movement. Suppose we have that rain we discussed before, the rain falling because of the air resistance. There was air, so it must experience a drag upwards, right, when it's moving down, so that it makes this real motion of this rain become a changing acceleration, a variable acceleration movement. Another case was, we have a spoon. Spoon at the end have an object. If it do a simple harmonic motion, its movement equation is x equals a cosine omega t plus phi 0, which this a is the amplitude. And this is called angular frequency. And this is the phase, the initial phase, v0. So that to take the one-time derivative, we can get v equals minus omega a sine omega t plus phi 0. Take a second derivative, we got a equals minus omega square a cosine omega t plus phi 0. And we found it exactly minus omega squared x. And we will discuss this later on in the 7 chapters about the vibration and wave, which we will strengthen a lot on those stuff. But here is just a brief little introduction.